Okay, hi everyone, I'm Bonnie Waiwan. I'm from Carnegie Mellon University and CCA. Today I'm going to talk about my work on machine learning cosmology from void properties. So from Linder's talk, you already know voids are the less dense regions in the galaxy distribution. And there have been some current constraints from voids from the Bell surveys. With the void galaxy cross-correlation functions, we are able to constrain the meta density. And also with the void size function, we're able to constrain both omega m and sigma 8. So these constraints seem to be very promising from void statistics. While there have been already some models to extract information from voids, there are still some underexplored void properties. So machine learning models are very great for these underexplored statistics. So this work is about applying machine learning models to extract information from the void catalog and predict the cosmological parameters. So let's first to talk these void properties. So as you can see, void can have very different morphologies when we have different ellipticity of voids. And the void ellipticity is also a bit correlated from void size function, as you can see from the bottom plot. And the void density contrast is a ratio between the minimum density along the ridge of the voids and the minimum density inside of the voids. This property is more correlated with void radius as expected, because usually larger voids, they are more evolved and thus they're more deep. So the data set we use in this work is from GIGANTES. It is created by applying the Witt void finder on halo field and using the data from Quixote simulation. So first, we use a simple machine learning architecture, fully connect layers, to apply this architecture to the histograms of the void ellipticity and void density contrast. And in order to not just get a single value for the cosmological parameter, we use the loss function from the moment network so that we get the mean and standard deviation for the predictions. So this is the results we got. So from using only the histograms of void ellipticity, we're able to constrain omega matter. And with only the histogram of void density contrast, we are able to constrain both omega matter and sigma 8. And since the nature of the void catalog, they have a set structure, we also apply a more complex model, deep sets, to void catalog and do the same predictions for cosmological parameters. So for the deep set model, we use 3 void properties: void ellipticity, void density contrast, and radius. And as you can see from the plots, we're able to constrain omega matter, sigma 8, and the spectral index NS with 10%, 4%, and 3% error. And these are showing very promising directions. So the future works for this would be, first, we're now only using voids in real space in simulation. We want to use the voids in redshift space so that it's more similar to observations. And we also want to explore what if we combine the voids with more traditional statistics like cluster information. And also we need to test our models from different simulations so that they're not just overfitting to the training data we have. And finally, we want to apply them to the real surveys so that we can constrain the real universe. And thank you so much.